Okay, welcome everybody to the latest F-band network webinar. This month we're hearing from Mika Peace and the team of Harvey, Jesse and Jeff on access fire, the coupled WRF model. We've known for quite some time that the upper atmosphere and the fire behaviour are strongly coupled, and the work that this project's been doing is quite pleasing to me, at least, to see that we're finally getting some of the models connected, so that will lead to at least being able to better understand what happened on those days that we know about. But it's a significant step forward in terms of being able to better forecast those days. So I won't hold up too much. I'll hand over to Mika, but I'm certainly keen to hear what the team have to say.
Thanks, Mike. All right, so Harvey's going to be flying slides for us, so hopefully the slides pop up any second now. They haven't on my screen yet. But I'll start off by saying that, just by introducing the team. So we're going to share the presentation today. Myself, Harvey and Jesse are going to talk. Jeff's going to be in the chat, so if you've got any questions that you'd like to ask in the chat as we go, Jeff will be responding to those. So please keep him busy in the chat. It's a pretty small team who have been working on this. We've been going since the beginning of 2016, and for most of it, we've been working on other projects as well. So what we're showing here over the past few years of work has really been achieved with a pretty small team. So it's interesting to think what we could do faster with the capability that we've got with a larger team. I'd also like to acknowledge Beth Ebert, who is the head of our WEP team here in the Bureau, and she's been the sponsor of the project. And some of you will know that we've had a lot of technical issues, particularly in the first couple of years of the project. That's taken a lot of effort, particularly by Harvey, to overcome, and Harvey's going to talk about some of those. But it really has taken the support of people like Beth, and also from the CRC and from our end users, to really keep on persisting with trying to get this model working. And it has been a long-term objective. It hasn't been easy, but it really does show that when we're doing this kind of science, it is important that people have a long-term view and are willing to stick with us to overcome some of the technical challenges, because it really has been worthwhile. So I'd also like to acknowledge the CRC. Obviously, this is a project that's been done in parallel with the Bureau and the CRC, and with the support of a lot of end users. So we've had end users, obviously some of whom are online around the country, who have been supporting the project and also being involved in the project as we go. So next slide, thanks Harvey. So some of you will have seen the next slide before. This is the pyrocumulonimbus cloud that developed over the Waroona fire on the first day. It's a video that was taken by a guy called Darren McCarg. It's actually a time-lapse photograph. But what it shows is the incredible complexity of fire and atmosphere interactions. And the main point here is that this fire wasn't just occurring at the surface. Its energy source wasn't just at the surface. It's what we categorise as a plume-dominated fire rather than a wind-dominated fire. And the instability in the atmosphere above and the wind structure in the atmosphere above was a massive factor in driving this fire. If we look at the closest automatic weather station, which was dwelling up automatic weather station, looking at the FFDI numbers, at the time this video was taken, they were between about 15 and 19, which means that you should have been able to put out the fire with a fire truck and a couple of hoses. The maximum in the FFDIs on that day was 40 at 4:04 in the afternoon. So the question is, what can we understand about what was going on with the atmospheric processes and the convection column above this fire? Next slide, thanks Harvey. So the big question, of course, is can we model these processes? Can we actually have a model framework that can actually resolve all of these complex processes that are going on in between the fire and the atmosphere? And I think, as I was saying, it hasn't been an easy road the last few years getting this model up and running. Nobody in the outset said it was going to be easy, but to obviously channel the Coldplay song, which is appropriately called The Scientist, no one ever suggested that it was going to be as hard as it has been to get the model up and running. But But as we will see, it has very much been worthwhile. And Harvey's going to talk a little bit about the reasons that it's been difficult to get the model running. But I think there's a couple of things. Firstly, that the two models are actually, what we've done is we've coupled an atmospheric model with a fire spread model, and it's a purpose for which neither were originally designed, but also it goes across different spatial scales. So our atmospheric models normally are working on the scale of kilometres to tens of kilometres. Our operational model at the moment is 1.5 k's, whereas as many of you will know, the fire spread models are going down to tens of metres. So we've got this mesh of different spatial scales, and we've also got two models which were designed to do completely different things, and we're meshing them together. The important thing, I think, is that when we actually start to look at the output from these simulations, even though you might expect that it shouldn't work because it wasn't designed to be run in this way, we actually get results that match really well with the observations that occurred. And obviously in a fire environment, it's really difficult to take observations. So having a model capability that we can reset to different fires and examine the processes that were going on is really useful for understanding what's happening and then developing predictive techniques for the future. Okay, Harvey, next slide, please. So effectively, the basic premise is that we're looking for the fire and atmosphere interactions. So the fire releases energy, and what that does is it actually modifies the surrounding atmosphere. So the atmosphere doesn't passively drive the fire, it responds to the fire changes the surrounding atmosphere, and then that impacts how the fire behaves. And this is different in different cases, and it's particularly, you see these modifications over topography. So you've got a fast running grass fire over flat terrain. A lot of the assumptions in terms of the atmosphere driving the fire are going to hold, whereas if you've got a lot more complexity, if you've got more energy released in heavier fuels, you've got complex terrain, you've got different wind regimes happening through the topography, the modification process is going to be stronger. And what we see is that these dynamic feedback loops can have a really dramatic influence on how a fire evolves over time. So what we're using here is access fire. It is the Bureau's research and operational numerical weather prediction and climate model. So there's massive advantages to using the access model for this rather than some of the other international capabilities that are available, because access links so strongly to what we're doing in Australia in terms of weather research and forecasting and climate. So by using the access model, it directly correlates with what we're doing in all of the other environmental, weather and climate space. So the model itself was originally developed in a collaborative project with Monash and Melbourne universities. They used it to simulate the Kilmore East fire on Black Saturday, and at the bottom of the slide there I've got the publication that they did using access fire. So that was in 2018. So if anybody's interested in looking into the capability and seeing the work that's been done, that one's available. And we're also in the stages of drafting up the 2 case studies on Waroona and Sir Ivan that I'm going to talk about today. Thanks, Harvey. So the first of our case studies is the Waroona fire, which was south of Perth in January 2016. There were 166 homes destroyed. There were 2 fatalities the second evening of the fire. And in total, over the 4-day period that the fire burnt, there were 69,000 hectares burned. Importantly, in the first 2 days of the fire, there were 4 periods of extreme fire behaviour. There were 2 pyrocumulonimbus clouds that developed over the fire, and there were 2 evening ember showers, the first of which impacted the town of Waroona and the second of which impacted the town of Downslope. Now, importantly, these extreme fire behaviour periods did not reconcile with the maximum in the FFDIs. So there was a mismatch in the timing between the extreme fire behaviour and when the FDIs were indicating that you should have seen the worst conditions. So in particular with the coupled model, what we wanted to do was look at the ember showers over Waroona and Downslope, and also look at how well the model can produce the deep moist convection or the pyro-CV above the fire. Thanks, Harvey. The second fire was the Sir Ivan fire, which was in February 2017 in New South Wales. It burned 55,000 hectares. There were 55 homes lost. At the time, it was described as the worst fire conditions ever in New South Wales. Obviously, this is before the season that we've just had. The fuels at the time were extremely dry due to severe drought. And importantly, in this case, there were no surprises in terms of the fire behaviour. The catastrophic conditions were identified several days out. The numerical weather prediction models did a really good job of capturing the weather on the day. And so what we wanted to do in this case was really try and unpack and examine the processes that were driving the fire. It wasn't a case of people were surprised by the fire behaviour or it was unexpected, but it was a really complex event. And in particular, we had quite a marked shift from the northwest to the southwesterlies in the wind change in the afternoon, and there was quite a short-lived pyro CB that developed, so we wanted to look at that as well. So next slide, thanks Harvey. So before I pass over to Harvey, I just want to compare and contrast the two pyro CB pictures that we just looked at. So the one on the left is the Waroona one, the one on the right is the Sir Ivan fire. And hopefully what you can see there is that there's really different structures to the cloud and to the convection columns over the fire. So the Waroona one was quite vertically stacked, was quite an organised convection column. There was quite a lot of rotation in the wind shear, which meant that it was vertically sitting over the fire. Whereas the Sir Ivan one, there was a lot of wind in the northwesterlies and the shallow southwesterly change came through and undercut the northwesterly winds. So what you can see in the photograph there is you've actually got quite a lot of shear. So you can see the change in direction in height with the different structure layers of the cloud as it's being driven by the wind. So with the Waroona fire, the lightning strikes actually happened quite close to the fire, whereas on the Sir Ivan fire, they were quite a long way downwind because by the time the cloud had developed to the top of the atmosphere, it had been blown quite a distance from the actual surface fire. So that raises questions in terms of what potential feedbacks or what potential influences are you going to see from the structure of the cloud and the convection column above the fire in different wind regimes. So I'll pass over to Harvey now. He's going to talk a little bit about the model itself and what we've been doing with the Access Fire model, and also some of the challenges that we've had to overcome in terms of reconciling the two modelling regimes. Thanks, Harvey.
Thanks, Mika. So as Mika mentioned, the original code was developed in Melbourne Uni, Monash Uni for Black Saturday simulations, and it was an older version of the atmosphere model. So we are going to use it in the modern version of the atmosphere model. Logically, the system can be divided into two main parts. One's atmosphere model, the other one is fire spread model. So the coupling, the meaning of coupling is shown in this block diagram. For each time step, atmosphere model will feed the surface parameters such as wind, surface temperature, and relative humidity to the fire spread model, which will calculate how the fire will spread, as well as the heat flux, which will be fed back into the atmosphere model to affect the simulation for the next time step. As Mika mentioned, we normally use sub-kilometer scale for the fire simulation, but the atmosphere model, especially the global atmosphere model, running at more than 10 kilometers scale. So one of the challenge we need to meet is the scaling down of the simulation. So we've arranged 4 nests, scaling down from 4 kilometer to 1 kilometer to 300 meter and 100 meter. So the coupling doesn't happen for all those scales. We only apply the coupling to 300 meter and 100 meter scales. The simulation will run on NCI, on Region, and later on Gardi. For atmosphere model, we base on the so-called unified model, which is developed in the UK Met Office, and it's the same model we use in operational forecasting, which is called access. So it's why we call our model access file model. So the nesting, we use a standardized nesting suite, which provide a convenient way to scale down from the global scale into 100 meter. As I mentioned, there's 4 steps scale down to keep the ratio low enough to keep the model stable. Yeah, we've met a lot of challenge in keeping the atmosphere model stable when we have a strong heat flux input. So we spent quite a long time to try different settings according to guidance from model experts, as well as some educated trial and error. Eventually, we found that these 2 settings are critical to keep the model stable while we have the most intensive file. The first one is the convective, the boundary layer stability function should be set to standard LEM as opposed to conventional LEM in the default setting. The next one would be the transition RI for sharpest function should be increased to 0.3 instead of 0.1 as in the default setting. The file model code is a group of Fortran source code files, and we need to manually embed the group of files in the source tree of the UN standard land surface model, which is called the Joint UK Land Environment System, or JUICE. Now the call to calculate or transfer files related information has to be added in that source file in the standard source tree. The orography we use in the file model is interpolated from 1 arcsecond or 30 meters SRTM data, which is satellite image data. One of the most important component of the file model code is the calculation of the file spread rate. We have a range of spread models can be used, such as the CSRO, MacArthur, and Rosemo. After consultation with our partners in fire and land management agencies, we chose CSRO forest formula for our simulations. So the formula is shown on screen. As we can see, the fire spread rate is closely related to 3 parameters called hazard scores, FHS underscore S, FHS and S, and HNS. Again, with the consultation with our partners, so we we've chosen those scores carefully. And for Waroona, we use a surface field hazard score as 3.5, a near surface field hazard score as 2.5, and near surface field height as 20 centimeters. As we can see from the simulation result, this can give us very realistic fire spread behavior. I'll copy over to the next screen of the formula. We can also see that this fire spread rate is closely related to RH, relative humidity, and T, the temperature. Now these values should be the values of the environment and the non-fire affected environment. But if we do the coupling, these values will not be available in the current grid point. So we have to find a way to try to use close value to the environment value from the fire affected values. Now, in the original code, the mean value of the relative humidity and the surface temperature in the 2 by 2 kilometer box centered at the current pixel, current grid point is used. In our simulations, we found this this method could still lead to unrealistic and unsustainable fire spread rate. So after a bit of trial and error, we found that by using the maximum value for the relative humidity and minimum value for the surface temperature in the current subdomain, which is around 7.5 kilometer by 7.5 kilometer box for the 300 meter scale, or 2.4 by 2.4 kilometer for the 100 kilometer box scale. So this can give us much more realistic spread rates. Other than that, the major difference between the original code and what we use now are listed here. First, we introduced switch on and off course to the code so that the switch on and off can be according to something like a resolution instead of hard-coded, and then we have to maintain multiple copies of the executables and code them according to different resolutions. And the second, we have added an option to have a user-defined polygon as the initial fire shape, in addition to the circular and the bar shape starting shape, and this enabled us to simulate fire whenever we have a non-fire parameter to have more detailed simulation and more accurate simulation at that point. Next, we enabled automatic model restarts and maintain the time consistency. So this allowed us to have far less human requirement for the human intervenes in the actual running of the simulation. Then next we introduce the high resolution, same as the orography data, the 300-meter scale water body data, so that whenever we see a grid point is water, we don't allow the fire to burn over it. So over to Jesse. He's going to talk about the simulation result, analysis result.
Thank you. Hello. So here we've got a good sort of overview of the Waroona fire. So first we'll talk about the Waroona case study. Waroona is just a bit south, a few hours south of Perth on the west coast. So here on the left of the plot, you can see the coastal plains, which is farmlands and rural towns. And you can see Waroona and Yarloop are there, dotted and labeled. Then in the middle, from north to south, there's a around 300 meter escarpment that rises up, and then to the east, it's sort of state forest and a few mining areas. And over in the east there, you can see is where the fire ignited. And here the red contour lines show the first day of fire spread. And this is the estimated outlines. This is not from the model. This is what was estimated to be the actual spread of the fire. So you can see that first day it spreads pretty much directly towards the west, and then it spots, and on the first evening, it actually makes it down the escarpment and runs into the sort of residential areas there. So on that first day, it spreads quite fast, and there's a pyro CB and a downslope run. And we want to look at all these things, but first, if we go to the next slide, we want to compare the fire spread between the model and what we actually think the fire spread is. So if you go to the next slide, Harvey. Thanks. Here, the bottom picture shows the simulated fire front. The red contour lines there is the hourly fire front. And if we really look at the red contours, you can see that it's a pretty good match between the two figures here. Fire spreads to the west, and even at the end of that first day, you can see the fire has made this big run down into the populated area. So that's a pretty good result there for the fire. It makes it all the way down. It's worth noting here that the initial fire polygon is set by Harvey manually, and any spotting is also set manually here. And then the yellow contours here sort of show the second evening of the fire, and no manual fire breaks sort of in the model. The model is just what would happen if there was no fire prevention methods. And they also pretty well match the fire spread. So if we go to the next slide. So now the first thing we looked at was, okay, is the atmospheric part of the model producing these pyrocumulonimbus clouds? So this is 4 time slices starting at the top left, where you can see the escarpment there, and you can sort of see the ground underneath. And then there's these red turrets, and they are the vertical motion. So there's some strong vertical motion there that you can see. And that's right at the fire front. So the fire is really driving this updraft. That's in the bottom 2 kilometers of the atmosphere. And then in the top right plot, this is 20 minutes after that first plot. And you can see the cloud is starting to form, and it's just being driven by this fire updraft. And then bottom left is 40 minutes later. The fire is still driving these updrafts, and you can see this cloud has just exploded up into the atmosphere. And it's really, I'd say, generated a pyrocumulonimbus at this point. And then half an hour later, you can see it's still generating this cloud. It's still pushing more energy and moisture up into this cloud, but the cloud is also sort of starting to spread out. So the model is definitely showing these, these big plume events going on. So if we jump to the next slide. What we wanted to look at with this plume was sort of the vertical motion. We really wanted to get a good understanding of what's going on in the model. So here, these plots show vertical motion. Pink is upwards motion, and then green is downwards. So the first panel here at the top is again a top-down view of the area. And you can see these dashed lines. They are where I've taken transects in this picture. And you can see the ignition over there on the right. And there's a red outline of the fire front at this point in time in the model. And at the fire front, you can sort of see there's generally upwards wind motion at that fire front. And if we go to the next panel, you can see this is the transect, the long transect, and it shows the vertical motion up to 15 kilometers altitude. And you can really see there's the red feature there. That's the upwards vertical motion in front of the fire, and it extends all the way up to 15 kilometers. So here that energy is really driving all the way up through this cloud. And the black outline there is the cloud. And you can also see around the pink, there's a lot of downdrafts. And these are really clear all the way down to the surface. So this is definitely plume driven at this point. And then the next two panels are just the smaller transects, but it's really clear these updrafts and downdrafts that are occurring. So if we jump to the next slide. The next thing we wanted to look at was the downslope run that occurred on that first evening. And Mika is going to discuss this in more depth. I'll just mention that we did see it in the model, and in front of the fire, there's a lot of atmospheric turbulence driven by the fire. So if we jump to the next slide. I'll also highlight that if you turn the coupling off in the model, you really get drastic differences in the atmosphere and at the surface and in the fire spread. So coupling really makes a huge difference in this process. So let's jump forward. So the next case study was Sir Ivan, and here again is a estimate of the fire spread. You can sort of see it spreads eastwards and then northwards. And this is several hours northwest of Sydney, so New South Wales. So let's jump forward. Now here in the bottom left is the simulated fire spread. These are the hourly contours of the fire front. You can see it starts it expands to the east and then to the north. And this was a huge fire, but it does do a fairly good job of the actual fire spread here. These are pretty similar scales, the two fires there. So that's pretty good sign. The fire spread is working coupled to the atmosphere. So if we jump forward. So one thing we looked at with the Sir Ivan case study was the pyrocumulonimbus firepower threshold. So this is a theoretical estimate of, given a profile in the atmosphere, how much energy would a parcel of air need in order to sort of break through the LCL and start forming these pyrocumulonimbus clouds, these big thunderstorms. So if we jump forward, here we've again got a top-down view at the top. If we use the modeled atmosphere and sort of estimate, right, given this atmosphere, how much energy is needed to form a pyrocumulonimbus, we can compare that to how much fire energy is actually output and say, all right, if we've got more energy, then then we think we need to form a pyrocumulonimbus. Are we seeing it? So the second panel here, the dashed orange line is the estimated energy required. So this is that PFT, the threshold. So you can see for the first half of that panel, the atmosphere is actually not very conducive to these thunderstorms clouding. The required energy is really quite high. But then at around 4 o'clock, the required energy drops down. So this means the atmosphere is changing into a state where pyrocumulonimbus is perhaps more likely. There'd be less energy required in order to form these thunderstorms. And then the solid yellow, or the solid orange line here is actually the energy generated by the simulated fire. So you can see here, I've circled in red this window of time where the energy generated in the model is actually higher than the energy required, the theoretical energy required in order to form these pyrocumulonimbus. And what we see actually is that at this point in time, this is both when a pyrocumulonimbus occurred in real life, and we do see that same formation occurring in the model. So this was a pretty positive result for the simulation. It's definitely capturing the atmospheric turbulence and the pyrocumulonimbus is occurring. And all this sort of happened around the time of a wind change that occurred locally. So in the bottom panel here, you can see the 10-meter winds, the average 10-meter winds over the fire area, and 500-meter winds. So it's about the time of a wind change. So that's what happened. Now if we jump forward, and then here's a picture. So at that point in time, this is basically what occurred. At the fire front, there's this massive updrafting of heat and moisture, and it's bursting through into the atmosphere. And you can see this, the pyrocumulus is forming right up to about 13 kilometers here. Yeah, and that's also associated with these big up and down drafts at the fire front for that brief period in time. So that was a pretty good result, I thought. And that's it. I'll pass it back to Mika.
Thanks, Jesse, and thanks, Harvey. Hopefully you can hear me again. We're all good. All right, so I'm going to talk a little bit about the downslope wind processes and what we found from that, and then talk a little bit about what happens next for the modelling capability. So for the next couple of slides, apologies to those who were in the FBAN New South Wales training a couple of weeks ago, because we're going to recap a bit of that. What I wanted to do was look for a nice definition of downslope winds, and I couldn't find one. They're not really neatly defined anywhere in the literature. Some people talk about them as a katabatic flow, but I think they're quite distinct in that a katabatic flow is effectively when you've got colder air at the top of the mountain, warmer air at the bottom of the mountain, and you get this gravity-driven flow, which is typically light if you've got a shallow mountain. It can be quite strong if you've got a long, steep mountain, but it's actually quite distinct from the downslope wind process that we're talking about here in terms of driving the fire behaviour. Another definition, or another definition that people talk about, is the idea of föhn winds, which really have a rain shadow effect. So the whole idea with a föhn wind is you've got air which is lifted on one side of the mountain, it forms cloud, the cloud produces rain, so you've actually got air mass going down the other side of the mountain, which has got quite different properties to the air mass that was going up, because you've lost all of the moisture in the rain process. So it's not quite that again. Probably the most useful definition is that of downslope windstorms, and what we see is, particularly when you've got a ridge of high pressure, a high pressure system rather than a low pressure system, you get layers, particularly in the overnight period in the atmosphere. So when we've got a low pressure system, things tend to be quite well mixed through the boundary layer, whereas when you've got a high pressure system, you've got a lot more stratification in terms of what's happening with the different temperature and wind layers. So what we see with downslope winds is we've got this diurnal cycle of the low level wind maximum, which is sitting above the surface. So typically it mixes out during the day and it intensifies overnight. What we can often see above topography is that you've got a temperature inversion sitting, and what that can do is act as a lid which squeezes the wind. It's probably not the best scientific definition, but it effectively squeezes the wind maximum between the top of the top of the topography and the bottom of the inversion, which means you've got acceleration of the flow fitting through the gap between the two layers. You can get really rapid onset of downslope winds, and they know this because they've done transects with little planes near where they've got airports to look at how quickly these downslope wind processes can start up and then dissipate. So you can get quite rapid onset, which has obviously got implications for fire activity. They tend to be most favourable where you've got long, gentle windward slopes and steep lee slopes. And what you get in these processes is a really highly dynamic flow. So you've got a lot of turbulence, you can get hydraulic jumps, and you can get rotors. And what all that adds up to with the turbulence process is that you've got the mechanism for lofting embers. And importantly, they can interact with a fire plume. So wind interaction with topography is an important factor in a lot of significant fire events. I've listed just a few there, not just in Australia, but also overseas. And if you look at that list, you'll see that a number of those are also where they're associated with fatalities. And that's because part of the reason for that is because it's unexpected and also it can be quite rapid onset. So the downslope wind processes contradict two main assumptions. The first is that the fires typically are expected to spread slower downslope. Obviously, if you've got fast downslope wind and turbulence, you can increase that spread. And also the assumption of reduced fire activity overnight, because typically when you see these wind maximums, it's in the overnight period. Harvey, next slide, thanks. So I'll show this schematic. This was done by the forecasting team in the Perth office a little while ago as a public information piece. But what it does is show really nicely some of the processes that are going on in a downslope wind environment. So this is a cross section across Perth City, where you've got the Perth Scarp to the east, you've got the very flat coastal plain to the west, and then you've got the water over the beach. And this is in the overnight period. And what you've got is this low level wind maximum, which is sitting above the surface, and the topography perturbs the flow of that wind maximum. So you can see a couple of things here. Firstly is that the strongest wind's sitting just above the topography on the lee slope. And what you can also hopefully see here is the level of the wind maximum isn't very far above the surface. So I think the topography there is around about 400 or 500 metres, and the wind maximum is sitting just above that. So it's well and truly inside the height that we'd expect to see entrainment or mixing through a fire plume. Now, importantly, from thinking about what we get out of the incident weather forecast and the ADFD grids, so the digital forecast grids, if you look at what's happening at the surface there, you've got a really marked difference in the wind speeds at the surface compared to what's happening in the jet maximum. So your wind speeds at the surface are around about that 5 to 15 kilometre an hour mark. That's what's going to show up in your surface grids. The wind speeds above that in the maximum are above 100 kilometres an hour, so there's a really tight gradient in there. And importantly, and we'll see this again in the next slide, is that that wind maximum can actually be below the level that we show in the incident weather forecasts, which is typically the wind speeds at 100 metres. So you can get, at 1,000 metres. So you can get quite a shallow jet, a shallow wind maximum, which is sitting in between your surface winds and your 1,000-metre winds. Next slide, thanks, Harvey. So this is a plot that Alex down in Tassie did for one of the New South Wales fire reports. And the reason I wanted to show this is it's an example of what the forecasters, so the embedded mets and the fire weather forecasters can pull out from visual weather. So this is what we can actually look at operationally in real time. So what Alex has done is a cross section, which is along the transect that's shown in the satellite picture on the right. So that's our transect, and obviously we're looking at it across the topography in New South Wales, and that's up to a height of nearly 10 kilometres. So down the bottom bit, obviously we've got the topography, we've got the pretty flat coastal plain on the eastern edge of the plot, but what you can see in here hopefully is this really distinct gradient again in the wind from the surface to sitting up at a height of around about 1,500 metres. So at the surface, we've got really light winds. Winds are around 5 to 10 knots. That's what's going to be coming up in your forecast grids. Sitting above that, particularly over the topography, you've got a wind maximum of over 100 kilometres an hour, so over the 50 knot mark. So you've got this really sharp gradation in the wind maximum, and as we'll see in the next plots, the fire plume can mix that down to the surface. So important to think about, this is the way that we can actually visualise this in real time, and the way that we can interrogate the numerical weather prediction grids to actually look at what's happening above the surface. Next slide, thanks Harvey. So just to recap where we were looking at with the Waroona fire, we've got Waroona and Downslope marked there in blue. So both evenings, the fire coincidentally happened to be coming down the scarp area in the evening period as the downslope winds or the overnight winds picked up. Now, importantly, both of these, both evenings, at Waroona at about 9 o'clock on the first night and at Downslope at about 7:30 on the second night, there were ember storms reported at both sites, which obviously had a massive impact on the firefighting activities. Now, just to make a distinction here, that what the reports were very much about ember showers or ember storms rather than isolated spots. So if we think about the two different spotting processes that can happen, one is where you've got spots that are lofted up in the fire plume, they're transported downstream by the winds above the surface, and then you get isolated spots that can ignite new fires kilometres to tens of kilometres downstream. Whereas what we were talking about and the descriptions that were happening in this scenario was that we had mass transport of a lot of embers much shorter distances. So it's completely consistent with a really strong turbulence mechanism, which is lofting the embers locally and transporting them hundreds of metres or potentially a couple of kilometres, but transporting large number of embers rather than that isolated long distance spotting. So we're talking here about short distance mass spotting events rather than long distance isolated spotting events. Thanks, Harvey. So just going back to what was happening in the winds above the surface, this is a plot similar to what Jesse showed before. The blue box shows the area that he's averaging the parameters over. The second plot has got our temperature and the relative humidity and also the cloud. But what I'd like to do is draw your attention to the bottom plot, which is showing the average winds over that box. The grey is at 10 metres and the beigey orange colour is at 500 metres. So important there, look at the distinction. The maximum winds at 500 metres and at 10 metres were in the evening period and overnight, and the minimum in the winds at both levels was in mid-afternoon, where you typically expect to see the maximum in fire danger or in your FFDIs. So maximum FFDIs is minimum environmental winds above the surface. When you're expecting to see your lowest FFDIs in the overnight, that's when you've got the highest winds above the surface of 500 metres. And just to make the point that if you were paying attention when Jesse was showing the plots of this Sir Ivan, we actually had quite a different process going on, different synoptic system, where you had the maximum in the 500 metre winds that was happening in the middle of the afternoon with the passage of the front, and lighter winds in the evening period. So there's quite different mechanisms depending on what your synoptics are. Next slide, thanks Harvey. So what happened at Waroona? This is the cross sections from the period around about the ember storm. So we've got 10-minute increments from 9 o'clock in the evening through until 9:30 in the evening. The top plots show the cross sections that we're looking at. So there's 3 different cross sections. The one on the left column is the coupled simulations, and the one on the right column is the uncoupled simulation. So we've run the model twice. The first time the atmosphere knows that there's a fire there. The second time the atmosphere doesn't know that there's a fire there. So it's effectively working as a 2-dimensional spread model. So importantly, when we look at this, what we can see is that in both cases, the model is picking up the wind maximum above the surface. But when we turn the coupling on, what happens is that that wind maximum comes closer to the surface. So instead of being at an elevation of between 500 and 1,000 metres, the wind maximum is sitting right above the surface driving the fire. And it's also increased. So instead of seeing lighter winds near the surface and the jet maximum sitting above it, we've got winds that are around about the 80 kilometre an hour mark sitting just above the surface, and those are the winds that are driving the fire front. So if you can just step through for us, Harvey, please. So you can see it's a bit of a transient feature. So every 10 minutes, the pattern changes a little bit, so it's very dynamic. It's showing that it's very dynamic in terms of the response to the fire. And keep stepping through, thanks Harvey. And what you can also see, particularly in this plot, if you look at the middle plot on the left column, you can see the wave motion showing up in the streamlines there. So that's an indicator of the really strong turbulence that we're seeing, and obviously that's a very strong mechanism for localised transport of firebrands. And what we know from the reconstruction of the Waroona fire is that in the evening period on the second day, as it went into Yarloop, the fire ran into an area of very heavy fuels, which was obviously firstly conducive to favourable for an increase in fire intensity, but also favourable for an increase in firebrands. So if you just go through to the next slide, thanks Harvey. Thank you. And again, if you look at what's happening in terms of the difference between the coupled run and the uncoupled run and focus at what's happening just above the surface, you can see that any uncoupled forecast information is going to give you near surface winds that are around about the 10 to 12 metre of second mark, whereas the coupling process is bringing winds which are closer to 70 to 80 kilometres an hour close to the surface. So really important implications in terms of overnight fire activity and fire behaviour. Next slide, thanks Harvey. So on the second evening, as we said, the fire burnt towards the town of Yarloop, but in the reconstruction in the report, one of the key things here was that there was actually a decrease in fire activity in the afternoon period. So the fire activity in the afternoon was pretty quiet as it ran down the scarp, so they weren't expecting an increase in fire activity into the evening. So what we've got here in these two plots is on the left-hand side is the fire intensity. This is from heat flux from output from the model. The fire intensity at 4 o'clock in the afternoon, which is obviously around about your time of maximum FFDI. And then the plot on the right is in the evening period, and you can see that there's a very marked increase in fire intensity. And noting on the scale here that this is a log scale. So from the afternoon period to the evening period, you had 2 orders of magnitude increase in fire intensity. And obviously that was as it went off the scarp and down onto the coastal plain. Now, if you look at the streamlines in here, those streamlines are the black lines. They're the wind, got the wind arrows on them. You can see that the streamlines here, they're plotted for speed in terms of the thickness. So there's not that much difference in terms of the near surface wind speed from the afternoon period into the evening period. But what you can see from the thicker black lines on the right-hand plot is that the wind speed near the fire front was much stronger in the evening period. That's what's driving the fire intensity, and that's the direct consequence of the entrainment of the mixing down of the winds from above the surface. Okay, thanks Harvey, next slide. So as Harvey mentioned, we used the CSIRO forest model for the Waroona case, and we ended up using the same for a lot of the Sir Ivan case because we'd had good results from it. And Lockie worked with us to come up with the numbers for this. So Lockie provided numbers for both the Waroona case and also for the Sir Ivan case. And I think that the remarkable thing and the thing to really note here is that in both simulations with pretty much no adjustments or no calibration factors, we ended up with a really good match for the fire reconstruction and for the simulations. So we really didn't make any adjustments to it. We just plugged the numbers that Lockie provided into the CSIRO model in the coupling and ended up with results which are a really good verification for what actually happened. So a pleasing result, obviously only from 2 different cases, and we'd need to look at it more systematically to establish that it's going to work in all cases. But in some ways it makes sense because Vesta was designed to look at the high end of fire activity. So it's quite probable that implicitly it's actually capturing some of the mixing processes of winds above the surface because it was actually experimentally designed to be done in those higher end conditions. Thanks, Jessie. Thanks, Harvey. So as part of the reporting for the CRC, we've just recently done the annual reports and asked for end user statements from both John Bally and from Lawrence McCoy. And both of them highlight, firstly, the complexity of running the coupled model, but also both of them make comments about potential use of access fire or coupled modelling capabilities and operations. So just John's bottom line on that slide there. And Harvey, if you flick to the next slide, please. Again, in Lawrence's end user report, talking about how do we build in some of the findings into predicting extreme fire behaviour, but also potentially an operational coupled fire atmosphere capability in the future. Next slide, thanks Harvey. So as a result of the Monash and Melbourne project and also this CRC project, we have Access Fire, which is an Australian capability for fire meteorology research and potentially in the future for real-time prediction. So what we really need to do now, I think, across the fire meteorologist group and the FBAN group is think about how do we firstly apply the learnings to fire prediction in terms of what we do now in our current processes, and in the future, where do we want to go with the next generation of fire simulators. What we know is that in a changing climate, we're going to see increased fire risk and increased impacts of bushfires. And also we've seen this recently from the past season, but also coming out in the Royal Commission, is that there's increasing community expectations in terms of the information streams that we can provide. And there are obviously implications for bushfires, but also for managing the risks and certainly anticipating the risks in prescribed fire or hazard reduction burns. It's also not just an Australian problem. There's growing wildfire impacts internationally. And with Access Fire, we've got a capability which has links to all of the UN partners. So all of the different partners around the world, the different Met agencies in different countries. There are a number of places that use the same modelling framework that we do, that Access Fire is linked into, and they include places like the United Kingdom, obviously, but also South Africa and Korea and Singapore. And as we now see the CRC transition to the new Research Centre for Disaster Resilience, one of the questions is what kind of capability do we want to develop in coupled modelling as we move forward? Next slide, thanks Harvey. So what we saw in the past summer in terms of fire behaviour was a lot of fire behaviour which links pretty directly back to some of the coupling processes and the feedback processes that we're seeing in the coupled model. So we saw a deep moist convection on a number of days, and I think it's really reassuring that with very different approaches, both the Access Fire model and Kevin's PFT work have got really nice overlaps in the way that they've come together. So there's a lot of consistency there, which is really reassuring. The downslope winds, I think, is a challenge that we probably need to embed more systematically in the processes, in the way that we do the forecast and the predictions. And we saw a number of cases in the past summer where we saw fire spread overnight that was driven by the above surface winds, and particularly in heat waves. So that overnight fire activity is a challenge not only in Australia at the moment, but also in the USA, and they're doing research work about that. We also saw fire-generated vortices in the past summer, and we haven't shown here, but on the Sir Ivan fire later on in the afternoon as the wind change went through, we actually got small little rotation areas which were showing up in that, and which is also consistent with other work that's been done in the States with coupled fire atmosphere modelling. So there's certainly the potential for looking at these fire-generated vortices using the coupled model. So in the short term, we can look at different training that we can do for both the FBANs and the embedments and the FireMets, and identifying and developing tools and techniques to look at when are these coupling processes likely to occur, and how do we include that kind of information in our operational briefings and our incident weather forecasts. In the medium term, can we include some of the processes as flags maybe, or triggers in some of the two-dimensional simulators that we're using, such as Spark? And in the longer term, do we nationally want to develop a fully coupled operational capability, which wouldn't necessarily be used on all fires, because we know that some fires is probably not going to provide value in terms of the computational investment, but certainly in other cases then that it would be useful and valuable. And I think the other thing to think about that when we look at the operational paradigm is that at the moment we've got, and if we look at the past summer, we certainly had F-bands who are running probably dozens of simulations of different fires on a given day. And some days there were probably simulations or predictions for hundreds of fires happening across the country. And it's taken us the better part of 4 years to run 2 simulations that we've just shown today. So it's a pretty big step up in terms of getting access fire operational. So next slide, final slide. Thanks, Harvey. So obviously we're going to see increasing challenges in the future in terms of seeing fires across the continent and also in the prediction space. But I wanted to show this photograph of the Mount Solitary prescribed burn because I showed this at an F-band workshop a little while ago, and somebody else actually showed it first. One of the other guys showed it first. But the important point was that he had a completely different story about it to tell compared to what I did. So I look at this and I see a smoke level beneath the inversion and convergence into a convection column and then cloud above the lifting condensation level. And he was talking about ignition patterns and burn objectives. So the point is that we see, as F-bands and meteorologists, we see completely different things in the same picture, and I think it really highlights the need to work together in the future and collaborate, because we've got completely different areas of expertise that come to play. So I'll finish up there. Thank you all for joining. Hello to those who we haven't seen for a while. It's nice to at least know you're online virtually, even though we can't get together in real life, and hope everyone's keeping well. Back to Mike. Thanks.
Thank you, Mika, Harvey and Jesse. Are there any questions for Mika or the team?
If you have questions, if you could click on the raised hand icon, and I will unmute you so you can put your question directly to the panelists.
You've stunned them into silence, Mika. I assume that's a good thing.
Hello, can anyone hear me?
We certainly can, Tony.
Yeah, Tony Smith over in Western Australia. I just had a general question. I was really interested in the graph that showed that you could theoretically calculate the energy required to generate the pyro-Q. And I was just wondering if there was a sort of an intermediate step between having a fully blown coupled atmospheric surface model, whether how hard would it be to calculate a rough index, given you've got a going fire, you have some idea about its rate of spread, intensity and heat generation, and getting a ballpark idea as to, look, this is likely to couple with the atmosphere or it may not, as just a general addition to our perspective on the fire?
Yeah, well, that's largely Kevin's PFT work. I don't know if you've seen any of the output from that, or whether you've seen the webinars that he's done. He's done a couple of presentations. So that's another CRC project. And that's effective. What you're talking about is effectively what he's been doing. So he's been using output from the access model, high resolution operational NWP model, and he's been running it in real time and effectively calculating for a given environment how much energy does the fire need to release in order to get deep moist convection. So that is coming into an operational trial this season. So Kevin's working with the CRC to put that in operations. We did last summer trial it unofficially, I guess, in a number of different states. So we were looking at it in New South Wales operationally, and we were also looking at it for a little while in South Australia. But that's going to be rolled out across the country. I think in Western Australia, it probably hasn't had the same amount of exposure as what it has in the eastern states, but more than happy to get Kevin to talk to you. And I know that he has been in contact with Gianni, who's our embedded met over there. Jeff might want to add something else there on the project.
Yeah, good question, Tony. Yes, as Mika says, we ran the trial over the last summer. And, you know, when you run a trial of a new forecasting technique, of course, you always hope that something will happen. And the last summer was absolutely amazing for pyrocumulus. We got good indication of the event on just about every event, just about every observed pyrocu. And there were a couple of cases with very unusual boundary layer structures which didn't quite get there, but it was a very, very successful trial. And we're very encouraged at the skill of the system, and we're getting a lot of support from the agencies over here. So we're trying to push that into operations. I should add that Kevin's also had quite a bit of interest from the US, as you'll have probably seen. There's been a lot of PyroCB events in California and Oregon over the last month or so. And so he's in contact with the Storm Prediction Center people in the US about them using the PFT as well.
Excellent. Thanks very much. I'll follow that one closely.
Mika, there's a question from Lockie. What is the potential to use access fire couple runs to look at the sensitivity of fire behaviour to fuel inputs?
Yeah, good question. So one of the things we didn't discuss today, but which is in the paper that's in preparation, was for the Sir Ivan fire, we started off with the same set of numbers in terms of the Vesta inputs that Lockheed provided for Waroona, and we got a PyroCB, and then Lockheed provided another set of numbers which was slightly less, and with the lesser heat generated with those fuel numbers, we didn't get a PyroCB. So it shows really reassuringly that we're kind of on the threshold of having the right heat fluxes in the model coming out from the fire component, going into the atmospheric component to either produce deep moist convection or not. So it does show that with the current settings, which I think is fortuitous, which is great, that we're actually getting that sensitivity around about right. We've also had some conversations with Melbourne University, and they're keen to look at access fire in a separate project to try and understand and unpack a little bit more about the deep moist convection processes on a fire and how much the convection is actually going to or likely to feed back onto the fire ground. And this sort of goes back to what I was talking about before, is that is the wind shear above the fire going to convect the plume downwind, or is it likely to be more upright and then therefore have more of a likely impact in terms of having downdrafts, which can then affect the surface fire. So understanding that process, I mean, we have had a bit of an assumption that if you're going to get deep moist convection, then it will impact the fire ground, but nobody's actually systematically looked at that. And Jay and Brian in the States wrote a nice little paper a little while ago, which was quite a short paper, really saying that nobody's actually set out the links between deep moist convection or pyrocumulonimbus, whatever you want to call it, above a fire, and how that actually directly affects the fire behaviour. So what we do have in access fire is a capability where we can start to look at those things more systematically and do a whole series of testing. And there's also the potential to take the fire model out of the numerical weather prediction model and put it back into a simpler idealised model, and then test a set of cases which can then look at the different sensitivity thresholds. So lots of interesting work to do, and obviously we've only run a couple of cases on it, which tells us about those cases but doesn't necessarily give us the ability to extrapolate to all situations.
Thanks, Mika. And just one for Tony. Kevin did do a webinar earlier this year, and it's on the AFAC YouTube channel, so that might be a place to start. Were there any other questions?
Yeah, I'll give it a go. Hello, Mika. G'day, Andrew here from Queensland.
Hello.
There you go, Mika. Good to see you. Jeff, I'm doing a study of people's backgrounds and all the virtual meetings I attend, and you scored pretty well. Good bookshelf there. So given we've done 2 simulations over the journey, and one was a standout, you know, Sir Ivan, easy to pick. We need to know for every resource we possibly can at that situation. But the other one at Waroona, fantastic tool post-fire reconstruction to understand the fire behaviour. But how else do we know prior to the event that this is an event we want to be looking at? What's the flag for that one, do you reckon?
I think the flag for that one in the future is really looking at the increase in wind speed in the overnight period sitting above the topography, and the fact that the fire was going to be moving down into the lee slope, or on that kind of interface between the topography and the coastal plain in the overnight period. So it's the wind above the surface, I think, which is really important, but also some of the stability information. And I think that's where we need to start moving away from just looking at the surface parameters, particularly in instant weather forecasts. But it also, I think, then means that we've got to have the embedded METs and the F-bands sitting alongside each other, having that back and forth conversation about where's the fire going to be overnight, what is the weather going to do, what's that going to do to the fire, and what's that going to do to the weather. So I see that for the next year or two at least, because we're not going to have a capability that can simulate these things for us operationally in the next couple of years. So for the next couple of years, it's about training our F-bands and training our embedded METs and our fire weather METs to understand these processes and look for what the flags are. And effectively, it becomes pattern recognition. But I think that the interesting thing is that for me, going around the country and talking to different people, is that different people can say, oh, well, I remember that because it matches what I saw in this case. So the pattern recognition component is really quite strong, particularly for people who have been in the game for a matter of years or decades, where, you know, we do accumulate this library of different scenarios, and then that becomes sort of the frame of reference for what's going to happen at the next fire. So I think there's definitely that training piece. It's definitely about looking up and making sure that we've got people who are looking at more cross sections in real time rather than just focusing on what's happening at the surface. And then in the longer term, it's about how do we include flags in the simulators that we've got now, or the simulators that we're developing in the future, so that we know when we need to look out for the coupling processes. And then maybe down the track, we've got an operational couple model to look at the worst cases in real time. But I think also there's links back to some of the hazard reduction burns as well, and the fuel reduction burns, because the ones that I'm aware of in the last few years, which have produced unexpected fire behaviour, it hasn't been because of the winds that were there, it's been because of what the atmospheric stability was. So I think there's a lot of potential for adding value to the outcomes and to the risk assessments in hazard reduction burns, in terms of looking at some of these coupling processes and seeing if any of them are likely to eventuate.
Thanks, Mika. Love your work. Keep it up.
Thanks, Andrew.
But again, this is another point where things get a bit turned on their head. Now, Mika's already talked about the fact that the fire becomes more active towards the end of the day when you're normally expecting things to calm down a bit. Normally you expect stability is something that, you know, again, tends to reduce the fire activity. But in this case, the increase in stability with the lateness of the afternoon is actually crucial to setting up the downslope winds. So it's, you know, it's not one of these your normal situations, your normal experience is going to support you. Your normal experience is actually going to lead you in the wrong direction when you've got these type of events where the increase in stability, the increase in the wind late in the day, and suddenly you've got your worst activity right when you're not expecting it.
Yep, thanks, Jeff.
Any other questions? I'll take that as a no, and then thank Mika, Harvey and Jesse and Jeff for their work and for their presentation today. It's certainly it's quite an exciting project definitely in a research space, and while it's not going to give us tools tomorrow, it's certainly good to see some progress in that in the atmospheric coupling space, because we know it's a problem, and we've obviously got Kevin's work, but extra work to try and progress identifying indicators and potential predictions of those events is very important for our firefighter safety, let alone the community safety. So I thank everybody for attending. This will be on the YouTube site in about a week or so. If other people, if you know of people who you think should see it other than the group, or you want to look at it again, thank you very much. Thanks to Ben for running the background processes, and we'll talk to you again in a month or so when the next one is. Thank you.
Thanks, everyone.
Cheers.
Thanks, all.
Bye.
See ya.